Hello everyone, I'm Sebastian, and welcome to the MATLAB and Simulink robotics arena. In this video, we'll talk about getting started with Simulink and the Robot Operating System, or ROS. And I'd like to introduce Pulkit.
Hi, I'm Pulkit. I'm the Senior Industry Manager for Robotics and Autonomous Systems at MathWorks.
Okay, thank you. So in this video, Pulkit and I will talk to you about how to combine Simulink with ROS. This is actually the second video in 3 parts. So the first part covered getting started with ROS and MATLAB. Then we have this one on Simulink, and then we'll have a following video on deploying algorithms to ROS. More specifically to this video, we'll discuss the workflows possible between Simulink and ROS, and then we'll look at a couple of templates and an object tracking example. And we'll wrap it up with some key takeaways. Before we jump into our presentation, we'll jump into an object tracking example using a robot. So this robot is following a blue circle. It is tracking both the distance away from itself by looking at the area in pixels of the blue circle and trying to keep itself a certain distance away, and also trying to keep the circle centered in its field of vision. Okay, so now let's talk about the Simulink and ROS workflows. There is an interface between Simulink and Robot Operating System. The reason that we want to be using Simulink is because it provides quite a bit of functionality that is used for tasks like developing controls algorithms, perception, and planning and decision making. It's also used quite extensively for simulation, so it could be the other way, that you have some algorithm that's created externally and you're connecting it with a simulation in Simulink. Regardless of what that connection is, there's 2 main ways to interface between ROS and Simulink. The first one is what we call a desktop prototyping approach. And that's where you can have a Simulink model as you're running a MATLAB session that is communicating using ROS to some of these simulators, hardware, or other ROS nodes. But in addition, there is a deployment workflow where you can take your Simulink model and generate it via C or C++ code into its own standalone ROS node, so that then whatever algorithm you are developing in Simulink is now running standalone outside of the MATLAB environment. And both of these are possible with the Robotics System Toolbox. And in this video, we'll focus on the desktop prototyping workflow, since we have the following video will be on deployment. If you've watched the previous video, great. If not, we'll recap that whenever you're developing some kind of algorithm that connects to ROS, there is a setup component where you're establishing a connection between MATLAB or Simulink and ROS. And then you have what we call the control loop, which is continuously sensing data over the network, doing some kind of processing or algorithm, then sending out commands or control signals back out through ROS. And there's an optional visualization step that might happen in the middle for debugging. And in MATLAB, we showed you how you can do this with code. However, in Simulink, the alternative is to do this through a block diagram.
Yeah, that's right, because Simulink is a graphical programming language, so you can easily represent these steps in your workflow as independent blocks for sensing, processing, controls, and you can visualize any of those blocks through the visualization capabilities like plotting or the camera output.
Right. So why don't we actually jump right into one of the templates we provide for Simulink, because we could be talking about what the blocks look like, but I think it's easier to just go look at them.
Yeah.
So going into the template files, I'm just going to make sure that everything's added to my path, and I'm going to open up one of the first simulation templates. As you see here, all of the boxes in this model have to do with those steps that we discussed, so sense, process, control, and visualize. And for all of those sections, you could have blocks or even subsystems that contain multiple blocks containing each of these functionalities. The one thing to note here, which is important, is you'll see these blocks that I've highlighted, which say ROS on them. These come from the Robotics System Toolbox block library, which provide blocks that can directly read or subscribe to topics, as well as create messages and publish them through ROS topics. So this can it lets you really communicate with ROS without really having to write any code.
That's great.
Now, the one thing that we need to talk about is the setup section. So where do you initialize the connection between Simulink and ROS? And where do you load things like parameters, for instance? The way we do this is actually through what is known as model callbacks. So I'm going to jump into that by going to File, Model Properties, and within this menu, you'll see that there's going to be a Callbacks tab. And in this case, we've populated the preload function callback, which is a common one to fill in. This is MATLAB code that will execute whenever you open up the model. So what we're saying here is that when we open up the model, we're going to use ROS init to initialize a connection to ROS master or to start one. And then I've also created a couple of other parameters that denote, for example, sample times or control gains.
So the setup is the same as what we did for MATLAB, except now we use the preload function and use the MATLAB commands in there.
That's correct. The other difference between this and MATLAB is that in MATLAB, we talked a lot about scheduling the algorithm and figuring out what rates these things run at. Simulink, on the other hand, is quite good at handling multi-rate systems. So I want to show you a slightly different variation of this model, which might even be a more realistic approach for what you folks are doing that are watching. And this is going to be a multi-rate template. So this preload function for this model is a little bit different. If I go over here, you'll see that there are two variables called sample time slow and sample time fast. And they are different sample times, as their name suggests. We're using these two variables to define sample times in our model. And the way we're doing that is by going into the subscribe blocks. So if I double click one of these, you'll see that the sample time is set to sample time slow. And then if I go to the other one, then it's set to sample time fast. Now,
sample time slow and sample time fast are variables in our MATLAB workspace.
That's right. And we can verify them by looking into the MATLAB workspace. So you see that they exist over here, as I've highlighted. If you enable this option, which is display sample time, you can actually display in a color-coded and labeled way what the sample times throughout this model are. So actually, by enabling this option and then updating our model, my model is now color-coded, and I have a little legend here, which tells me that everything that's in green or labeled D2 is the slow rate, and then everything in red or labeled D1 is going to be the fast rate. And in between, you've got this rate transition block, which is the yellow one. It's not only easy to define different rates in Simulink, but you have utilities like these to visualize how this ends up looking on a block-by-block basis, because you want to make sure that the correct blocks are running at the correct rate as you're designing these algorithms. Okay, so you saw how this was designed in Simulink for a very simple example. And then we also saw how you can create multi-rate systems by defining different sample times in blocks, and then the other blocks will then inherit those sample times based on the rules of Simulink.
So why would we want to use multi-rate systems versus running it as fast as Simulink can?
One of the key applications is when sensor data comes in a lot slower in one case and faster in the other. I'm thinking, for instance, if you have, like a wheel encoder, you might get data pretty quickly from that encoder. But if you have a point cloud, those might come in an order of seconds. So you don't need to be processing things, equally as fast all throughout the board. So typically, your perception algorithms might be running slower than your low-level control. And these could live in the same model. These could live in separate files. There's a couple of ways to do that. So what else can we say about Simulink? There are a lot of modeling languages in Simulink.
Yeah, so in Simulink, you can not only use block diagrams, which are very good for modeling control systems and signal flow, but you can, as we saw through the preload function, you can also use MATLAB code. And this is really good if you have legacy and existing MATLAB code that you can bring in into a Simulink model. And one way to do that is using the MATLAB function block. We see this a lot where algorithms are actually better expressed as code, where you have your pseudocode of your algorithm flow, and you can model this as MATLAB code, and you may want to bring that into Simulink through a MATLAB function block.
One example just from my experience for when MATLAB is really just a lot more natural than other things is doing a kind of sorting algorithm or a ranking algorithm. Yeah, and the third modeling language we show here is actually Stateflow. This is another add-on to Simulink, which lets you model logic-based systems like flowcharts or state machines, tables. There's quite a bit going on there. So typically we use these for things like supervisory control or scheduling. So really the summary here is that even though we say Simulink, doesn't mean that you're writing all your algorithms in Simulink. You really want to know the strengths of each of these three languages and make sure to use them together where it makes sense. Following this example, we do have a couple of other best practices for how to use Simulink effectively.
As we talked before, usability of functionality is an important construct in programming. It not only makes our code modular, but it also allows us to test individual components before putting all the functionality together. In our case, in Simulink, you can not only have your algorithms be separated MATLAB files, but you can also have separate Simulink blocks for the different functionality as we saw for sensing, for processing, and for controls.
Yeah, and by storing things into block libraries too, you're able to reuse the same algorithm maybe with different parameters in multiple places.
That's right.
Carrying on in the theme of separate files, we also talked a little bit about that preload function. Generally, it's good practice to also keep that as a separate script. That way, it's a lot easier to modify that script in that separate file in the MATLAB editor rather than go into the little callback window every time you want to make a change. And this is applications, as you'll see in the examples, where we're talking about having different preload functions for setting up interfaces to a simulator versus to a real robot, for example. So that being said, I think we can jump right into our software demonstration. So let's look at the demonstration files here. And in this case, I'm going to show you an example that connects to Gazebo. So in this case, we have a pretty big model here. It looks very similar in structure as the small template that we showed you before, right? Where we're receiving data from our subscriber. In this case, we're also using a read image block to actually extract all the image data from the ROS topic into a matrix. And then we're doing our processing, which, as we saw before, it contained the first part, which is the object detector or the vision algorithm, and that's being done with the MATLAB function. So in this case, we're just reusing that same detect circle function. And then the tracking portion is being done using Stateflow and Simulink. If I dig into the Stateflow chart, you'll see how this is done. In this case, we're actually using Stateflow for our supervisory logic. We have two what are known as parallel states that are performing two independent tasks. So the state on the left, highlighted here, that's the one that's looking at the image data that's coming in, and it's figuring out whether or not it's a valid reading or it's an outlier. And it's using a flowchart to count these all up. And then the part on the right is actually doing the tracking. It's using the information on how many outliers it has to figure out whether it should operate in a normal state or in an abnormal state where it's going to be scanning for an object unless it can't find one in a certain amount of time. Now, for example, if you look at the normal state, what we're doing here is while we are in the normal state, we're actually calling what is known as a Simulink function called vel control or velocity control. So this is a way to actually call Simulink blocks from within Stateflow. So this vel control is actually a collection of Simulink blocks that is shown in this box here. And this contains a proportional control with some decision, a little bit of decision logic expressed in Simulink blocks. And you see that this looks like your typical controls block diagram. So these are really two proportional controllers for the linear speed and for the angular speed of the robot. And these are all referring to parameters that are from our MATLAB workspace. Things like our param structure that contains different gains or target sizes or reference values. So all of this can be combined. Again, you'll notice here that Stateflow is used for the supervisory logic, Simulink is used for the low-level control, and then MATLAB is used for the vision algorithm. Okay, so I'm going to be running this model, and I'll minimize out of here and show you the two things that are happening. So again, on the left we have the image feed from the robot, and on the right we have our simulator that we're connecting to via ROS. And you see that now the object is centered in our field of vision. So I can move this around. For example, if I move the box close to the robot, it's going to be moving away. And if I move the box away from the robot will move towards it. And again, it will turn to make sure that that object is kept centered. The other thing that we can do is if the object is not visible, then the robot will turn and scan until it finds the object again. As this model is running, I can actually use the animation in my chart and take a look at what state the object is in. Let me actually zoom into the tracking state. You see right now that I'm in normal mode as far as tracking because we're seeing an object. Now, if I were to grab this and move it, say, behind the robot so it can't see it, eventually it's going to go into this abnormal state and it's going to be scanning for the object until it finds it again.
This is great for debugging.
Absolutely, and there's a lot more going on, right? If I actually go into, for example, our Simulink function that's doing all this execution, and let me scroll through to the right where I'm showing my linear and angular speeds. While the model is running, I can actually click some of these signals and display their value as my simulation is running. So right now you see that these two speeds are set to 0 because our object is perfectly centered. But if I start moving this around and I make the object move, you'll see that these values, you can see them updating in real time, which is pretty nice. Of course, there's the other Simulink visualization techniques that are available, like being able to put signals to scopes or being able to log them into the simulation data inspector. And of course, we can do parameter tuning, right? So if, for example, if instead of using this parameter as target size in here for the target size of our object, I could always go into this constant block during runtime, change that to a different value, say, and then the robot will update its reference as it's going. So there's a lot I can try out, and we'll actually see more of that too in our deployment video. Now, there's one piece that we haven't yet talked about, which is, being able to do this same kind of stuff with a real robot. So much like we discussed in the other video, in this case we have a model that talks to our gazebo simulator, which subscribes from a certain topic and sets up a particular IP address. But I could always reuse all of our algorithms are in the middle, so certainly our processing and our visualization. And if I just change the other blocks that are around this, I can create a model that will similarly work for a different robot. So for example, I've got the same model for the TurtleBot. And if I open this up, you'll see that the model looks exactly the same, except that I'm using, again, a different topic name. There's actually a different image encoding in the sensor. And then, of course, initializing to a new IP address in the startup. But as far as the algorithms, it should be the same thing with perhaps differently tuned parameters.
What about real-world situations that the robot has in terms of communication lags that might happen more on a real robot than in simulation? Are there any differences, or is the behavior pretty much identical?
A very good question. So I think that certainly depends on communication lag. That's going to be a big thing. That's one of the things you got to watch out for with ROS in general, right? You could actually have the same algorithm running with two different platforms, but simply changing the communication delays could impact your model. And that's true of many distributed systems or things that run in parallel, right? Nothing is really deterministic anymore unless you do some kind of handshaking yourself. So generally, you either want your algorithms to be fast enough, or again, you want to handle some of this handshaking with different kinds of communication practices. So let's see if that looks any different by jumping into this model running with the TurtleBot.
And if I move it closer, it moves back, keeps the distance the same. See if it follows me around. That's great. It's keeping the object centered in its field of view.
So what if you remove the object? Yep.
Like that. It should scan for it.
So it looks like it's stopped. It's waiting for a couple of counts. And then if it doesn't see the object for a little while, then it should start turning.
Yeah. Yeah, just
there
like
it is.
That.
And then if it sees the object while it's scanning, then it might pick it up again.
Ah, there it is.
Awesome. So we saw the object tracking example working with both a simulated and a real robot. Let's talk about some key takeaways then. Once again, we noticed that Simulink can support desktop prototyping workflows, but it also supports algorithm deployment, which you'll see in the next one. The other thing that we saw here was that you can create multi-rate algorithms by setting rates in different blocks, and you can actually have access to different tools where you can see what these rates were, just to make sure that you've implemented things correctly.
So that you can work with sensors that are giving information much faster, like encoders, and also with sensors like laser scanners that are providing point clouds at a much lower rate, and integrate both of these together into one algorithm.
Exactly. And besides that, besides the fact that you can schedule things in Simulink, we saw that with the Simulink model, you actually have exposure to 3 different modeling languages for different tasks, which are MATLAB, Simulink, and Stateflow.
Yeah, I think Stateflow is cool because it's the language of state machines, and whenever I start designing a robotic system, the state machine is the first thing that I would sketch out. Yeah, and I really liked how you showed the debugging part of Stateflow, because I can track in which state my simulation is running right now. So if I see a behavior that doesn't correlate to how I imagine it should be, then I know exactly where the error lies or where the bug might be.
Yeah. And to that note, I guess we didn't talk about it in this video, but it's worth noting to our viewers. In addition to just being able to view where you are in Stateflow, you can actually also put in debugging breakpoints. And that's true for MATLAB, Simulink, and Stateflow. All of them have a debugging functionality. I guess the last takeaway we talked about then was, much like in the MATLAB workflow, it's always a good programming practice in general to split things up into modular components. You want to make sure that if you have to make a change somewhere, it's only in one place, and that things are as reusable, unit testable, and as easy to use as possible. So again, thank you for being in this video, Pulkit. As always, feel free to contact us via email or Facebook, and check out some of the other resources below. Thank you.
Yep, thanks a lot.